So we're going to start by talking about a carboxylic acid, and then we'll finish talking about something that you can get with an alcohol that we learned about yesterday and a carboxylic acid that we will learn about right now. Now, chances are you've actually heard of a carboxylic acid before. You just didn't know that it was a carboxylic acid. And the reason I say that is because I think you have all heard of vinegar or acetic acid before. And it is a carboxylic acid. It's one of the most common acids that gets talked about and used, especially in our chem lab, because it's cheap and easy and relatively non-dangerous. I know when I teach Chem20, I use acetic acid or ethanoic acid, which is its correct organic name, as my example of a weak acid in most cases. So carboxylic acids are weak. Now we're going to talk about acids in general, not just organic acids, but all acids a lot in the last unit. So I just want to make sure everybody remembers. I've put my data booklet away. I'm going to grab one. In your data booklet, there is a table that has all of the acids that we typically talk about in it. You might have looked at it before just to see like what the name or formula for an acid is, but on page 8 and 9 of your data booklet, here's a list of acids. They're all there. And if you scan through, you're going to see that a lot of them have COOH on them. COOH makes them carboxylic acids rather than just plain old boring inorganic acids. So we're just going to talk a little bit about carboxylic acids. The data that's on those pages of the data booklet, there's numbers there. We don't use the numbers until Unit 4. But if you're ever looking for the names or the formulas for a carboxylic acid, a lot of them are there. The carboxyl group is where you have a carbon double bonded to an oxygen, then another oxygen, then a hydrogen. Now, what's on the other side of this carbon? We usually just put an R there to represent some other stuff. It could be 1 carbon, 10 carbons, it could just be hydrogen, but there's something else that's non-important in terms of function attached on the other side. So when these molecules ionize in water, it's that hydrogen that's going to contribute to the acidic properties of a carboxylic acid. Now you might remember in Chem20 talking about what happens when you put an acid in water. And while this is not the main point here, it really will be in Unit 4, because we'll talk about acids again. Anytime you have an acid and it reacts with water, the hydrogen from the acid will join water to make hydronium. So when I say it's ionizing in water, I'm referring to getting hydronium as a result of putting an acid in water. Now I hope you're all like, ooh, I love that part about acids and bases in Chem20, because we're going to do it again in Chem30, but with more. Oh. Or you're disappointed, and I'm sorry for that. Now, that's what a carboxylic acid is. It's an acid that has this carboxyl group in it. So that carboxyl is its functional group. So when we name and draw carboxylic acids and we're looking for the root, we're looking for the longest chain, like we usually do, that has the carboxyl group. The carboxyl group is the most important of all of the functional groups that we've seen. It would take precedence over a double bond, over an alcohol, over basically anything. So it gets to be named first. Just like with an alcohol, we'll figure out what the parent alkane was called by looking at how many carbons were in that chain. If there were 5, I know that pentane is the parent alkane. Just like with an alcohol, I drop the E at the end of the name, and I will replace it with oic acid. And there is an actual space there. So this is not one long, ridiculous, continuous word. There is a physical space between one part of the name and the next, the only time it's happened so far. Then we identify the prefix like we would have done on any other compound. We'll look for alkyl side groups on the main chain. The thing that's important to recognize here is that the carbon atom of the carboxyl group is always carbon number 1. It has to be. And if you look at the structure of the carboxyl group, hopefully you can see why. It's impossible that it's not the first carbon in the chain, because what's on the other side of it? Oxygens. If I'm going to start counting carbons, it will be the first one I count. I want to start counting closest to the carboxyl group. Well, it is the carboxyl group. So wherever the carboxyl group is, that's carbon number 1 all the time. Does anyone want to ask anything about the rules there? So we have some sample carboxylic acids to name. You'll notice I'm progressing in size order here. So the first one, if I look, has 1 carbon in the chain. So if this were an alkane, I would call it methane. I know that I'm going to drop the E, so instead of writing it and then erasing it, I'm leaving it off. Then I replace that E with oic acid. Now notice there were no rules about putting a number to tell me where the carboxyl group is, because it will always be carbon number 1. There's no other way for it to be. If I move to the next one, I have 2 carbons in the main chain. If this were an alkane, I would call it ethane. So I write ethane, but I leave the E off because I know I'm going to drop it. I replace the E with oic acid. I don't have to say where the carboxyl group is because it's always carbon number 1. Now, could someone tell me the name of the third one? Same pattern. Propanoic acid. Oic acid is always the ending. So propane, drop the E, oic acid. I know sometimes people forget you need the A and the N from the alkane. You think it's just prop, but we take the name of the alkane, propane, drop the E. Now the last one shows you an example of an acid that has a side group. So because this is my main chain, and there are 4 carbons, I would call this something butanoic acid. So I would like for someone to tell me what the prefix should be here. Yeah. Methyl and what number? I agree that it's methyl, but it's going to be number 2, not number 3, because this carbon has to be carbon number 1. So even though I never have to write the number of where the carboxyl group is, it's always carbon number 1. So this would be 2-methyl butanoic acid. I would always start numbering wherever the carboxyl group is. Does anyone have questions they want to ask there? So let's give it a try the other way around. Pentanoic acid. So when you're drawing a carboxylic acid, it's really up to you. I have a tendency to do what the examples did and draw my carboxylic acid group on the right of the molecule, because that's how I represent a carboxyl group. You don't have to make it be on the right. That's just my habit. Now it's the first carbon, which means there are 4 other carbons in the chain. And so it would look like this. The carboxylic acid, where the carboxyl group is, that carbon won't have any additional hydrogen attached to it. because it's double bonded to oxygen and it's got the oxygen on the other side. Now, if you want to try line drawings for carboxylic acids, which is fine, this one starts off the same as pentanoic acid. So you would put 2 lines and then your O, and a single line to OH, and they would kind of look like this. So there's a carbon here. Even though you wouldn't have to write the C, that's the end of a line, so there's a carbon there. So that's 1, 2, 3, 4, 5. That's what pentanoic acid as a line diagram would look like. And then I just need to add my branches. Since it says 2-methyl, this is carbon number 2, so there's my methyl group. 4-bromo, so 2, 3, 4, there's my bromine. So here's what I see, and it's why I highlighted it at the beginning. If there's a line diagram of an acid, people have a habit of forgetting that carbon right there because there's so much other stuff attached to it. So I don't know how to make you notice it other than to just continuously remind you there's a carbon right there in the line diagram. Now if I'm going to do the next one, propanoic acid, you don't always have to show the carboxyl group facing up. You could show it facing down. There's no rule that says you have to draw it upright like that. So when I started this one off, there are 1, 2, 3 carbons, propanoic acid. And on carbon number 2, there's 2 fluorines. Now the last one has a phenyl side group, which hopefully you'll remember means you have benzene as a side group. Here, benzene is the side group because the carboxylic acid is a more important functional group, so it gets to be the main chain. Yes? Oh, yeah, you're right. I was putting them both on carbon 2 instead of 2 and 3. Thank you. Now the last one, butanoic acid, I'll draw it with the double bond on the other side, even though it hurts my brain to do that. So if we're going to draw the carboxylic acid with the carboxyl group on the left, it's pretty typical to draw the OH as an H then an O, because the O is the thing that's attached to the carbon, not the H. And that's how you would see it depicted if it was drawn that way, say on a diploma, because they always draw it structurally and represent the atoms in the order in which they go. Since this is butanoic acid, there are 4 carbons. Remember, 1, 2, 3, 4. And then on the third carbon, so right here, we would put our phenyl group. And you can draw benzene that way, or you can draw benzene this way with the alternating double bonds, your preference. Okay, we're going to finish this. Unlike other things that we've seen before, the carboxyl group is not just polar, it's very polar, even more polar than just the hydroxyl group. So hydrogen bonds can form. The result is much higher boiling points. Than for other hydrocarbons or derivatives with the same number of carbon atoms. So for example, all of these compounds have 4 carbon atoms. Butane has 4, butan-1-ol has 4, butanoic acid has 4, and butanoic acid has a much higher boiling point than anything else. Way, way higher than an alkane. An alcohol would be like the second highest in terms of boiling point up to here, but carboxylic acids have the most polar group, so they have the highest boiling point. The other thing is that because they are very polar, uh, anything that's short are liquid, anything that's long starts becoming a waxy solid. So carboxylic acids have a different kind of texture than a regular acid would. An inorganic acid would tend to look solid and like a crystal, maybe if it was in a solid form, but these ones are waxy. The polarity also makes them very soluble in water, especially the ones between 1 and 4 carbon atoms. Now, unlike alcohols, where it was really the first 2 that were miscible with water, now it's the first 4, but the same thing happens to acids as to alcohols. As the chain becomes longer, now the nonpolar characteristics of the rest of it cause the chain to be less soluble. Anywhere from 5 to 9 carbon atoms are less soluble. You can still kind of dissolve them, but it's not as easy. As soon as we get to 10 or more, now we're back to being insoluble in water. Now, there's a little sentence at the end there, carboxylic acids are weak acids, so they. And I want to ask you, if you were going to check to see if something was an acid in the lab, what could you check? There's a few ways you could check to measure whether something was an acid. Daniel, yeah. So we could say they turn litmus paper red. And he also mentioned they have a pH that's less than 7. Anybody remember any other tests that you can do that would tell you that something is an acid? You might have done it in Chem30, yeah? They conduct. There's one more. Maybe your teacher did it as a demo. There'd be 2 tubes. One was a strong acid, one was a weak acid, and I'd put a piece of magnesium in it. No? No one remembers this? So, acids react with metals. Like magnesium, like zinc. The stronger the acid, the more bubbles you see when you put the metal in the acid. But those are all lab observations that you could make about an acid. And I'm mentioning this now because we're talking about organic acids, and like I said, we're going to talk about acids in general in the last unit. And you need to know, if you're talking about an acid, you need to know some of the basic tests that you would use for it. Now, does anyone want to ask anything about carboxylic acids? So last group of compounds, no more new ones after this, are esters. Esters are a derivative that contain this functional group. Now, at first glance, you might say, gosh, that looks the same as a carboxylic acid, but it's not quite the same. If you look here, I have this R, which I said before was some number of carbons on the other side. How many? Doesn't matter. I have a carbon double bonded to oxygen. I have another oxygen, but then over here, instead of hydrogen, like I would have in a carboxylic acid, I have another chain made up of some number of carbons. I represent it with an R with a little 1, so we would read that as R prime. It's another group of carbons. So when we're talking about an ester, you hopefully notice it kind of looks like a carboxylic acid. What really happened is that there was a reaction where we took a carboxylic acid and an alcohol. So to understand esters, you had to first know about carboxylic acids and alcohols, because knowing their names allows you to determine the name of the ester. Now, if you want to be specific about what is happening when we're reacting these two things together, a carboxylic acid, remember, has the carboxyl group. An alcohol has a hydroxyl group. Now I'm just representing the sides of both molecules with an R because there are some carbons. How many? Whatever. Some number of carbons. What's important is the functional group. And when the carboxylic acid reacts with the alcohol, here's what you'll see. The hydrogen from the carboxylic acid that it can ditch when it goes into solution, and the hydroxyl group from the alcohol leave. And they form H and OH, which is basically just a molecule of water. I left it written in that weird way so that you could see where it came from. Now what's left is this bit. So they're going to be attached to each other. Like this. So we took the carbons off of the alcohol and everything on the carboxylic acid except that hydrogen at the end and smushed them together, and the leftover pieces made water. Now, even though this lesson is not focused on the reactions of organic compounds, this is an example of a reaction that organic molecules do, and it'll come back in another lesson. And I just want to highlight water is inorganic. The fact that water is there is often the thing that separates the correct answer in a multiple choice question from an incorrect one. Lots of people would be able to correctly tell me that I get an ester, but might forget that water is also a product, and it's always a product. Now, once we take our acid and alcohol and put them together, and we get this weird ester thing, we have to know how to name it. So before I go there, anyone want to ask anything about the reaction here? Okay. So what are we going to do? Identify the root. It's the part of the ester that contains the carboxyl group. So you are looking for this that's what's left over from the carboxyl group, from the group that had the acid in it. Now, how do I know where the acid starts or which side of the molecule was the acid? Well, we know that anything on that side was from the acid. So you're looking for that double bond to the O because you know that this carbon was carbon number 1 in the acid. It had to be. It was always carbon number 1 because it was part of the carboxyl group. So what you're trying to do is figure out what acid made up this ester. So you're finding the name of the parent acid. Then, in the suffix, instead of oic acid, we replace it with O8, O-A-T-E, O8. Then, for the first time ever, the prefix will be something different. Whatever the alkyl group originating from the alcohol was. Now, what does that mean? Well, the alcohol had some carbons on it. Whatever number of carbons came from the alcohol and are now part of the ester, that will be the prefix. And there's a space. Never happened before either. A space between the prefix and the root, crazy talk. So, if we want to see what this looks like in action, we'll look at these examples. So, I look at the pictures and I see, there's a double bond to an oxygen and it's not at the end of a chain. It's not a carboxylic acid, must be an ester. I look for this group first that carbon double bonded to an oxygen because I need it to figure out the name. I know that there's a carbon right here, and that if this had been an acid, this would have been carbon 1, that would have been carbon 2, that would have been carbon 3. It's not an acid, right? It continues on the other side, but if this had been an acid, the carbon that makes the double bond to oxygen would have been the first one. So the name of the parent acid is propanoic acid. Now, I know that I'm going to remove the oic acid and change it. So I'm just writing it above so that you can see that's what I did. I figured that must have been propanoic acid. So instead of oic acid, I change it to propanoate. Now on the other side of the molecule, after I have my ester group, my carbon double bonded to an oxygen and then another oxygen, I have these two carbons, 1, 2. That's the alkyl group that came from the alcohol. Those are the carbons that were part of the alcohol before we made an ester. There are 2 of them. If I was naming a regular side group that had 2 carbons in it, I would call it ethyl. The only thing that's different is I leave a space and I don't have to say where it is because it has to be attached to that oxygen. So that is ethyl propanoate. Now, it won't be often that in addition to the ester properties, there's also another side group on one of them, but just in case there is, we'll do the next example. Always look for this piece first. That's where you start. The carbon that's double bonded to that oxygen was carbon number 1 in the acid. There's the 1, there's carbon 2, there's carbon 3. So just like the last example, I have propanoate there, but there would have been a prefix on the name of my acid. It wasn't just propanoic acid. It would have been 2-methyl propanoic acid. So there was a side group on my acid, so that has to be part of the name. Now, in addition to that prefix I just put on there, I have to add another piece of prefix to say what's on the other side. There are 1, 2, 3 carbons that came from the alcohol that joined with an acid to make this ester. So I would call this propyl space 2-methyl propanoate. Examples for drawing, you'll see the first 2 are just basic. The other one has a little side group on the acid, but like Agatha's question was, is it on the alcohol side? Not usually, because then you have a prefix within the prefix and it starts sounding all crazy. So if we draw ethyl butanoate, this is the root, so I would start with that piece first. Draw your carbon double bonded to an oxygen. Now, if you recall, a lot of the examples have it going this way. You don't have to. Left and right are just relative. You can always flip things over. But this is the group that goes in the middle. And on this side, there should be 4 carbons. The first one is the one that's double bonded to oxygen. Then there should be 3 more. Now you can certainly do line diagrams. Just keep in mind if you're doing a line diagram and you need to know how many hydrogens there are, that might be tricky. On the other side of this group, you put ethyl. Ethyl is CH2, CH3. That's ethyl butanoate. So folks, I sketched out a line diagram for those 2 structures. Methyl propanoate, so Methyl is this side where I have one line, so there's a carbon right here. Propanoate, 1, 2, 3. 3 carbons on the side that has the double bond to oxygen. Here, butyl, so 1, 2, 3, 4 carbons on the side here. And then methyl propanoate, 1, 2, 3. And on the second carbon here is my methyl group. Does anyone have questions about the drawings that they want to ask? The most common mistake with esters is mixing up which side is which. So when you look at ester questions, if say it's a multiple choice question and the answer was ethyl butanoate, one of the wrong answers will be butyl ethanoate. Always. It always is. So just be on the lookout and realize that we know that that's a common thing that people mix up and it's always one of the wrong answers. So just be careful with that. Now, last piece of business here, physical properties of esters. Because they have the double bond to oxygen, they're kind of polar, but there's no OH groups. So their boiling points are lower than similar sized alcohols and carboxylic acids. So if I was going to put the boiling points in order, it would go acids, alcohols, esters, alkynes, alkanes, alkenes. Highest up here, lowest down here. That's basically their solubility as well, except the first 3 aren't even soluble. And as you go through esters, alcohols, and acids, the acids tend to be more soluble than alcohols, which are more soluble than esters. Now, esters, because of their volatility, lets them smell. They generate aromas. A lot of fruity flavors come from esters. So oranges, bananas,